Hello there, and welcome to Nix's Documentaries, where history is written not just in books but in ice, where climate is not just weather over time but a force that shapes everything, every species, every landscape, every human. Tonight, we're not just looking at the past. We're walking through it, through frozen landscapes where mammoths grazed, where glaciers carved valleys, where our ancestors huddled around, surviving in a world so different from ours that it might as well be another planet. This is the story of climate. Not climate as an abstract concept, not climate as something that happens to other people in distant places, but climate as it actually is, the fundamental context for all life on Earth, the background against which evolution operates, the force that has driven mass extinctions and explosive diversifications, the rhythm to which continents dance and oceans rise and fall. And before we begin this journey through time, through ice and warmth, through extinctions and adaptations, I'd love to know, have you ever looked at a glacier, at those rivers of ice flowing down mountainsides, and wondered what stories they... Because ice is not static. It's a record, a library containing within it bubbles of ancient air, particles of ancient dust, chemicals that tell us what the climate was like when that ice formed, sometimes hundreds of thousands of years ago. Now, if this kind of exploration speaks to you, if you've ever wondered what the world was like when ice sheets covered continents, when sea level was, inhabit meters lower than today, when megafauna roamed landscapes now buried under cities, I'd be grateful if you tapped like or subscribed. It helps this signal reach others who look at the present and see echoes of the past, who understand that climate change is not new, that the Earth has always been changing, but that the rate of change we're experiencing now is extraordinary. And so settle in, feel the warmth around you, the comfortable temperature of your room, because we're about to journey into a world of cold, into the last ice age that gripped the planet until just 30 years ago. We're going to watch ice sheets advance and retreat, see species adapt or die, follow our human ancestors as they spread across continents, surviving conditions that would kill most of us in hours. We're going to see how climate has shaped the modern world, how it's shaped us, how understanding the past gives us insight into the future. The climate has a memory longer than civilization, longer than our species, longer than most species currently alive. It has witnessed everything, and tonight, in the quiet, we're going to listen to what it has to say. Let's start not in the ice, but before it, in a world that would seem strange to us. A world without permanent ice caps, without glaciers except on the highest mountains. This was the world of the Pliocene epoch, roughly 2.8 million years ago, before the current ice age began. And understanding this warmer world helps us understand both where we came from and possibly where we're heading. The Pliocene was warmer than today by about 10 degrees Celsius on average. That might not sound like much, but global average temperature is a blunt instrument. Regional differences were more dramatic. The Arctic was perhaps sure to stir degrees warmer than today. There was no permanent Arctic sea ice. The Greenland ice sheet was much smaller or possibly absent entirely. West Antarctica had little or no ice. Sea level was higher, perhaps 2 meters higher than today, flooding coastal areas, creating different coastlines, different geographies. Florida was mostly underwater. Much of the Netherlands, Bangladesh, major coastal cities, all would have been submerged. The world map looked different. The climate was also different in its patterns. The jet streams, the bands of strong wind that circle the planet, were positioned differently. Precipitation patterns were different. The Sahara had more rainfall, supporting grasslands and forests where now there's only desert. The Amazon was wetter. Monsoon patterns were stronger and life was different. Forests extended far into the Arctic. Where now there's tundra, there were boreal forests, pine and spruce and birch. Animals we associate with warmer climates lived at high latitudes. Camels lived in the Canadian Arctic. Giant beavers, 8 feet long, built dams across North American rivers. Three-toed horses, ancestors of modern horses, grazed on grasslands, but the Pliocene world was cooling. Slowly, over millions of years, the planet was transitioning from a greenhouse climate to an icehouse climate. Several factors drove this cooling. The positions of continents, drifting on tectonic plates, had changed. The Isthmus of Panama had formed about 10 million years ago, connecting North and South America, blocking the flow of water between the Atlantic and Pacific, altering ocean circulation patterns. The uplift of mountain ranges, the Himalayas, the Rockies, the Andes, had accelerated. Mountain building increases weathering, the breakdown of rock. Weathering of silicate rocks consumes carbon dioxide from the atmosphere. More weathering means less atmospheric company, which means less greenhouse warming. The configuration of continents also mattered. Antarctica had been isolated over the South Pole for tens of millions of years since it separated from South America about 10 million years ago. This isolation allowed the Antarctic Circumpolar Current to form, a current that flows around Antarctica, isolating it from warmer waters to the north. Antarctica cooled, ice accumulated, and the East Antarctic ice sheet formed, the oldest and largest ice sheet on Earth today. But the northern hemisphere was different. There were continents at high northern latitudes, North America, Europe, Asia, but they were connected to lower latitudes, preventing the kind of isolation that Antarctica experienced. The Arctic Ocean was mostly enclosed, surrounded by land, with only narrow connections to the Atlantic and Pacific. This geography would become crucial for ice sheet formation. As the Pliocene progressed, temperatures continued to drop. Glaciers formed in the mountains, in Alaska, in Scandinavia, in the Alps. These were local ice caps, not continent-spanning ice sheets, but they were growing. And then about Ardent Loop million years ago, something changed. The ice sheets began to grow in earnest, advancing and retreating in cycles, marking the beginning of the Quaternary period, the time we're still in, characterized by repeated glaciations. What triggered this transition? There's debate, but several factors likely contributed. Orbital variations, changes in the Earth's orbit and axial tilt caused by gravitational interactions with other planets, affect the distribution of sunlight on Earth's surface. These variations, called Milankovitch cycles, operate on timescales of tens to hundreds of thousands of years. When orbital variations reduce summer sunlight at high northern latitudes, snow that falls during winter doesn't completely melt in summer. It accumulates, compacts into ice, thickens into glaciers. Once ice sheets reach a certain size, they become self-reinforcing. Ice is reflective. It bounces sunlight back to space, cooling the region further, allowing more ice to accumulate. Atmospheric company R also played a role. By the start of the Quaternary, company levels had dropped to around Arbic Batters parts per million, low enough that orbital variations could trigger ice sheet growth. In earlier, warmer periods with higher company, our orbital variations weren't sufficient to create large ice sheets. And so began the Ice Age, or more precisely, the Ice Age we're still in. Because the Quaternary period, the past, Ardent Loop million years, is characterized not by constant ice, but by cycles of glaciation and deglaciation. Ice ages and interglacials, cold periods when ice sheets advance, and warm periods when they retreat. We're living in an interglacial now, the Holocene, which began years ago when the ice sheets of the last glacial period retreated. But we're still in the Quaternary Ice Age. Ice sheets still exist in Greenland and Antarctica. If orbital conditions change, if company R levels drop, glaciation could resume. Ice sheets could advance again. Though, with current company R levels rising due to human activities, a new glaciation is unlikely for tens of thousands of years. Understanding the Pliocene, the transition to the Quaternary, helps us understand our current climate. The Pliocene, with its higher temperatures and higher sea levels, might be an analog for our future if we continue emitting greenhouse gases. We're pushing company R levels higher than they've been in 10 million years. We're potentially recreating Pliocene conditions, but at a rate thousands of times faster than the natural transitions. Now let's jump forward past the early glaciations to the last glacial period, the most recent ice age in common parlance, though technically it's a glacial period within the larger Quaternary ice age. This glaciation began about Ibet Iserwoling years ago and reached its maximum extent about Arserlook, Ubek to Sergioling years ago, a time called the Last Glacial Maximum, or LGM. Okay? At the LGM, ice sheets covered vast areas of the northern hemisphere. The Laurentide ice sheet covered most of Canada and extended into the northern United States, reaching as far south as modern-day New York, Ohio, and Montana. It was enormous, up to 10 kilometers thick in places, containing so much ice that it depressed the Earth's crust beneath it, pushing the land down hundreds of meters. Now, the Cordilleran ice sheet covered the Pacific Northwest, British Columbia, Alaska. The Scandinavian ice sheet, also called the Fennoscandian ice sheet, covered Scandinavia, Finland, and extended into northern Europe, reaching Germany, Poland, Russia. The British-Irish ice sheet covered the British Isles. Smaller ice sheets and extensive glaciers covered the Alps, the Pyrenees, the Caucasus, the Himalayas. In the southern hemisphere, the Patagonian ice sheet covered southern South America. The Antarctic ice sheet was larger than today, extending to the edge of the continental shelf. Even mountains in New Zealand, Tasmania, and other temperate regions had extensive glaciers. The amount of ice was staggering. Estimates suggest that at the LGM, ice sheets and glaciers contained about 1 million cubic kilometers of ice, compared to about 10 million cubic kilometers today. This ice came from the ocean, evaporated from the sea surface, transported by atmospheric circulation to high latitudes, where it fell as snow and accumulated over thousands of years. The result was a dramatic drop in sea level. With so much water locked up in ice, sea level was about Ibite arses meters lower than today. Coastlines were vastly different. The continental shelves, now underwater, were exposed land. You could walk from France to England across what's now the English Channel. Indonesia, the Philippines, and mainland Southeast Asia were connected in a landmass called Sundaland. Australia, Tasmania, and New Guinea were connected as Sahul. Siberia and Alaska were connected by the Bering Land Bridge, a vast tundra landscape that allowed animals and humans to migrate between Asia and North America. The climate at the LGM was cold, much colder than today. Global average temperature was about 6 degrees Celsius lower than the pre-industrial average, but regional differences were much larger. Near the ice sheets, temperatures were perhaps 2 Celsius degrees lower than today. Summer temperatures in what's now New York might have been similar to northern Canada today. Winter temperatures were brutal, far below freezing for months on end, but it wasn't just cold. The climate was also dry. With so much water locked in ice, there was less moisture in the atmosphere, less evaporation from the oceans, less precipitation globally. Deserts expanded. The Sahara was larger, drier. The Amazon rainforest contracted, replaced in places by savanna and grassland. Lake levels worldwide were lower. Many regions that are humid today were arid. The vegetation zones shifted dramatically. The boreal forests, the taiga that today covers much of Canada and Siberia, retreated southward, compressed into narrower bands. South of the ice sheets in North America and Europe was tundra, treeless landscapes of grasses, sedges, mosses, lichens, similar to what exists today in the Arctic but extending much farther south. South of the tundra were mammoth steppes, vast grasslands that stretched from Europe across Asia to North America. These were not like modern steppes or prairies. They were unique ecosystems, a mosaic of grasses, herbs, and scattered shrubs, supporting enormous herds of large mammals. This ecosystem has no modern. It disappeared when the Ice Age ended, and with it when most of the megafauna tropical rainforests contracted. The Amazon was fragmented into isolated refugia, patches of forest surrounded by drier vegetation. African rainforests shrank. Southeast Asian rainforests were reduced. But some areas became more habitable. The exposed continental shelves, the Sahul, Sunderland, the North Sea, these were productive landscapes supporting human populations, though they're now underwater and inaccessible. The ice sheets themselves were not static. They advanced and retreated in cycles, responding to orbital variations, to changes in ocean circulation, to feedbacks in the climate system. Within the last glacial period, there were warmer intervals called interstadials. When temperatures rose, ice sheets thinned, and ecosystems shifted. Then temperatures would drop again, ice would advance, and the cold would return. These oscillations are recorded in ice cores, in ocean sediments, in cave formations. By analyzing these scientists have reconstructed a detailed timeline of climate change over the past hundreds of thousands of years, revealing a climate that was highly variable, changing on timescales from decades to millennia. The Ice Age world was harsh, challenging, unforgiving, but it was also the world in which our species evolved and spread across the planet. Understanding this world, understanding how our ancestors survived, how other species adapted or failed to adapt, gives us insights into resilience, into what's possible, into what we might face in a rapidly changing climate. Now let's talk about the animals, the incredible diversity of large mammals that roamed the Ice Age world. The megafauna, these were creatures adapted to cold, to the mammoth steppes, to the harsh conditions near the ice sheets. And many of them were enormous, larger than their modern relatives, larger than almost anything alive today. The mammoth is perhaps the most iconic. The woolly mammoth, Mammuthus primigenius, was about the size of a modern African elephant, standing about Sandan meters at the shoulder, weighing Sutu lotons. But it was built differently, adapted to cold. It had long, shaggy hair, up to 1 meter long, and a thick layer of fat, which was far below freezing. Its ears were small, much smaller than an elephant's, reducing heat loss. Its trunk had a flap of skin that could close its nostrils, preventing cold air from freezing its lungs. Mammoths had enormous curved tusks, up to 12 meters long in males, used for pushing snow aside to reach vegetation, for defense, for combat during mating season. Their teeth were specialized for grazing, with ridged surfaces that could grind tough grasses and sedges. As teeth wore down, new teeth would grow from the back of the jaw, pushing forward, replacing the worn teeth. An individual mammoth would go through 6 sets of teeth in its lifetime. Mammoths were not confined to one region. Different species lived across the northern. The Columbian mammoth, larger than the woolly mammoth, lived in what's now the United States. The steppe mammoth, even larger, was an ancestor of the woolly mammoth. Dwarf mammoths, isolated on islands like the Channel Islands off California and Wrangel Island in the Arctic, evolved smaller body sizes, some standing only about meters tall. But mammoths were just one group among many. The mastodon, a relative of mammoths and elephants but in a different family, lived in North America. Mastodons were smaller, stockier, with straighter tusks and teeth adapted for browsing on trees and shrubs rather than grazing on grass. They preferred forests and woodlands, while mammoths preferred open grasslands. Then there were the giant ground sloths. These creatures, some species weighing cetons or more, were relatives of modern tree sloths but lived on the ground. The largest, Megatherium, stood over centimeters tall when on its hind legs and could reach vegetation high in trees. They had powerful claws used for pulling down branches, for digging, possibly for defense. Ground sloths lived in North and South America, filling ecological niches similar to elephants or large browsers. The woolly rhinoceros, Coelodonta antiquitatis, was another Ice Age giant, similar in size to modern white rhinos, but covered in thick, shaggy hair. It had two horns, the front one sometimes over a meter long, flattened and blade-like, possibly used for sweeping snow aside to reach vegetation. Woolly rhinos lived across Europe and Asia, from Britain to Siberia, grazing on the mammoth steppes. Predators were equally impressive. The cave lion, Panthera spelaea, was one of the largest cats ever, possibly Certobifidus larger than modern African lions, weighing up to 70 kilograms or more. It hunted on the mammoth steppes, preying on young mammoths, horses, bison, reindeer. Despite its name, cave lions didn't live in caves occasionally for shelter, and many fossils have been found in caves where the animals died or were brought by scavengers. The cave bear, Ursus spelaeus, was another large predator, though it was mostly herbivorous, feeding on plants with occasional scavenging. Cave bears were massive, up to ling kilograms, larger than modern grizzlies or polar bears. They hibernated in caves, and many fossils have been found in cave deposits across Europe. Then there was the short-faced bear, Arctodus simus, in North America, one of the largest land predators of the Ice Age. It had long legs, suggesting it was a pursuit predator or a scavenger, and it may have been capable of running down prey over long distances. Some estimates put its weight at over 2 kilograms. The saber-toothed cats, the most famous being Smilodon fatalis, had enormous canine teeth, up to about centimeters long in some species, used for stabbing prey. These cats were ambush predators, probably targeting large, slow-moving herbivores, using their powerful forelimbs to wrestle prey to the ground before delivering a killing bite to the throat or belly. And there were many others. The giant deer, Megaloturus giganteus, also called the Irish elk, though it was neither exclusively Irish nor an elk, had antlers spanning up to Sandert low meters, the largest of any deer. The steppe bison, Bison priscus, was larger than modern bison, with longer horns. The aurochs, Bos primigenius, ancestor of domestic cattle, stood inhabit meters at the shoulder, with long, forward curving horns. In South America, there were giant armadillos, glyptodonts, with shells like Volkswagen beetles, giant capybaras the size of bears, terror birds, flightless predatory birds, some meters tall. In Australia, there were diprotodonts, marsupials the size of hippos, giant kangaroos, centimeters tall, marsupial lions, giant monitor lizards. This was a world teeming with large animals, a diversity of megafauna that dwarfs anything in the modern world outside of Africa. The biomass of large mammals, the mammoth steppes supported herds that might have numbered in the millions, migrating seasonally, shaping vegetation through their grazing, affecting fire regimes, creating landscapes. But this world was fragile. The megafauna were adapted to specific conditions, to the cold, to the grasslands, to the seasonal patterns of Ice Age climate. When those conditions changed, when the ice retreated, when climates warmed, when vegetation shifted, many species couldn't adapt fast enough. And there was another factor, a new predator on the landscape, one that would prove devastating to the Ice Age giants, humans. While mammoths grazed and cave lions hunted, our ancestors were spreading across the planet, surviving in some of the harshest conditions imaginable, adapting culturally and, to some extent, biologically, to life in the Ice Age. Understanding how early humans survived the glacial period tells us about human resilience, ingenuity, and adaptability. Anatomically modern humans, Homo sapiens, evolved in Africa roughly Sambitling years ago. For much of our early history, we remained in Africa and the Middle East. But starting around Tirling Tulur years ago, humans began to expand, moving into Asia, Europe, Australia, and eventually the Americas. This expansion occurred during the last glacial period, during some of the coldest phases. The humans who left Africa encountered environments radically different from the warm savannas, where our species evolved. They faced winters that lasted months, temperatures far below freezing, landscapes dominated by ice and tundra. How did they survive? Fire was crucial. The controlled use of fire predates Homo sapiens, going back perhaps 1 million years to Homo erectus. But for Ice Age humans, fire was not optional. It was survival. Fire provided warmth, light, protection from predators, a means to cook food, making it easier to digest and extracting more calories. Evidence of hearths, deliberately constructed fire pits, is found in archaeological sites across Europe, Asia, and North America. These weren't random campfires. They were carefully managed, located in shelters, in caves, or in structures built from mammoth bones and hides. Clothing was equally crucial. Humans are tropical animals adapted to heat. We have minimal body hair, we sweat to cool down, we struggle with cold. Ice Age humans needed insulation. They made clothing from animal skins, fur-lined garments, sewn with bone needles using sinew or plant fibers as thread. Now, the evidence for sophisticated clothing comes from various sources. Bone needles with eyes for thread appear in the archaeological record around Sissersonling years ago. Burials show people adorned with beads and ornaments, suggesting they were clothed in ways that allowed decoration. Depictions in cave art sometimes show figures wearing what appear to be garments. Shelter was another challenge. In regions where caves were available, humans used them, but caves weren't common everywhere. On the open steppes of Eastern Europe and Siberia, humans built structures from mammoth bones and tusks covered with hides, creating semi-permanent shelters that could withstand harsh winters. One of the most impressive sites is Meterik in Ukraine, dated to about Sturwarling years ago. Here, archaeologists found structures built from the bones of over Cource's mammoths, circular huts with walls made from skulls and long bones, roofs supported by tusks. These weren't temporary camps. They were substantial dwellings, suggesting long-term occupation. Food was always a challenge. In the depths of winter, plant foods were scarce. Ice Age humans were hunters, relying heavily on large game. Mammoths, bison, horses, reindeer, these were the primary prey. Hunting these animals required cooperation, planning, specialized tools. Humans developed sophisticated stone tools, not just simple hand axes, but specialized blades, scrapers, burins for engraving, points for spears, and later for atlatls, spear throwers, and arrows. Different cultures had different tool traditions: the Mousterian, the Aurignacian, the Magdalenian, each with distinct styles and techniques. Evidence of hunting comes from kill sites, places where animals were butchered. Some sites show evidence of mass kills, where entire herds were driven over cliffs or into traps. One famous site is Solutré in France, where the bones of tens of thousands of horses accumulated over centuries, suggesting repeated hunts at the same location. But hunting megafauna was dangerous. A mammoth or bison could kill a human easily. Success required cooperation, communication, knowledge of animal behavior, knowledge of the landscape. Ice Age humans weren't solitary hunters. They lived in groups, bands of perhaps Erstwusser's individuals, cooperating for survival. These groups weren't isolated. Trade networks existed, evidenced by materials found far from their sources. Seashells from the Mediterranean appear in sites hundreds of kilometers inland. Flint from specific quarries is found across wide regions. Amber from the Baltic reaches southern Europe. This suggests exchange, interaction between groups, possibly alliances, possibly trading partnerships. Art flourished during the Ice Age. Cave paintings, the most famous being those in Lascaux and Chauvet in France, depict animals in vivid detail: horses, bison, mammoths, rhinos, lions. The painters used natural pigments, ochre for red and yellow, manganese oxide for black, creating images that still resonate tens of thousands of years later. Portable art also appears: carved figurines, the Venus figurines, small statues of women with exaggerated features found across Europe, bone flutes, musical instruments made from hollow bird bones, some dated to over Cicercling years ago, decorated tools, engraved bones, beads made from shells, teeth, ivory. And this art suggests a rich symbolic life, a capacity for abstract thought, for storytelling, for ritual. The cave paintings were often in deep, inaccessible parts of caves, requiring light and effort to reach. They weren't casual doodles. They were deliberate, possibly ceremonial, possibly related to hunting magic, to shamanism, to beliefs we can only speculate about. And Ice Age humans weren't just surviving. They were thriving culturally, at least. They had language, though we can't know what they spoke. They had beliefs, though we can't know exactly what. They had social structures, leaders, specialists, shamans, perhaps. They were fully modern humans, cognitively identical to us, just living in a radically different world, and they were spreading. By Cicercling years ago, humans had reached Australia, crossing open ocean, suggesting boats and navigation. By Senderting years ago, they were throughout Asia and Europe. By Sturweling years ago, they were entering the Americas, crossing the Bering Land Bridge from Siberia to Alaska, spreading rapidly southward through 2 continents. This expansion, this colonization of the planet during the Ice Age is one of the great human achievements. It required adaptability, ingenuity, courage. Our ancestors walked into unknown lands, faced unknown dangers, and survived. We are their descendants, carrying their genes, benefiting from their resilience. Around Cicercling years ago, the ice sheets had reached their maximum extent. The world was at its coldest, sea level at its lowest, ice at its thickest. But then, slowly at first, things began to change. The climate started to warm, the ice began to retreat. The last glacial maximum was ending, and the world was entering a period of deglaciation that would transform the planet. The warming wasn't smooth. It was punctuated by cold snaps, by periods when the ice advanced again before continuing its retreat. But the overall trend was clear: temperatures rising, ice melting, sea level increasing. By about Surrey Tebet years ago, the ice sheets had retreated to roughly their current extent. The last glacial period was over, and the current interglacial, the Holocene, had begun. What caused this warming? Orbital variations? The Milankovitch cycles played a crucial role. Summer sunlight in the northern hemisphere was increasing, causing more ice to melt each summer. Less ice reflected less sunlight, causing more warming, causing more melting. A positive feedback loop. Changes in ocean circulation also mattered. The Atlantic meridional overturning circulation, the current system that brings warm water northward and returns cold water southward, fluctuated during deglaciation. When the circulation was strong, it transported heat northward, warming the northern hemisphere, melting ice. When it weakened, warming slowed or reversed. One dramatic event interrupted the warming. About Jolbite years ago, temperatures suddenly dropped, plunging back toward glacial conditions. This cold period, called the Younger Dryas, lasted about Urbeck years. The cause was likely a massive influx of fresh water into the North Atlantic, probably from the collapse of ice dams holding back glacial lake gases in North America. This fresh water disrupted ocean circulation, reducing heat transport to the northern hemisphere, causing rapid cooling. Glaciers advanced again. Tundra expanded. The climate patterns resembled the glacial maximum. But then, about years ago, temperatures abruptly warmed again, perhaps rising degrees Celsius in just a few decades in some regions. The Younger Dryas ended as suddenly as it began, and the world entered the stable warmth of the Holocene. The retreat of the ice sheets transformed landscapes. Where once there was ice kilometers thick, there was now land, rock scraped bare by the passing glaciers, deposited sediments, moraines, eskers, drumlins, all the features created by glacial erosion and deposition. The crust, depressed by the weight of ice, began to rebound, rising slowly as the weight was removed. This process, called isostatic rebound, continues today in places like Scandinavia and Canada, where the land is still rising, sometimes a few millimeters per year, recovering from the weight of ice sheets that melted thousands of years ago. And melting ice released enormous amounts of water. Sea level rose rapidly, flooding the continental shelves, creating the modern coastlines. The rate of rise was dramatic, averaging about meter per century for several thousand years, with periods of even faster rise when ice sheets collapsed. The Bering Land Bridge, the connection between Siberia and Alaska, was flooded about Ling years ago, separating the Americas from Asia. The English Channel formed, separating Britain from the continent. Sundaland fragmented into the islands of Southeast Asia. The North Sea flooded, submerging landscapes that had been inhabited for thousands of years. These floodings weren't just gradual inundations. Sometimes they were catastrophic. The Black Sea, for instance, was probably a freshwater lake during the glacial period, isolated from the Mediterranean, with a level much lower than today. When sea level rose enough, the Mediterranean breached the Bosporus, flooding into the Black Sea, possibly in a massive deluge that raised the lake level by over meters, drowning settlements around its shores. And this Black Sea flood hypothesis is debated, but if it occurred, it would have been a catastrophe for people living in the region, possibly giving rise to flood myths that appear in various cultures around the Black Sea and Middle East. Vegetation zones shifted as the climate warmed. The tundra and mammoth steppes that covered much of Europe and North America retreated northward, replaced by forests. Spruce and pine forests advanced, then broadleaf trees, oak, elm, beech, creating the temperate forests familiar in Europe and eastern North America today. But the mammoth steppes didn't just move north, they disappeared. The unique combination of cold, dry climate, grazing by enormous herds of megafauna, and fire created an ecosystem that couldn't exist in the warmer, wetter Holocene. The grasslands fragmented, replaced by forests in some areas, by different types of tundra in others. And with the change in vegetation came changes in fauna. Many species adapted, shifted their ranges, found new niches. Reindeer moved north, following the tundra. Bison persisted in shrinking grasslands. Some species thrived in the new forests, but many didn't make it. The megafauna, the giants of the Ice Age, began to disappear, and their was not gradual. It was rapid, catastrophic, and it left a world impoverished compared to what had existed for hundreds of thousands of years. Between roughly Wuserling and Serling years ago, the world lost most of its large mammals. This die-off, called the Quaternary Extinction Event or the megafaunal extinctions, was not uniform across the globe or through time, but the pattern is clear. Large animals, particularly those weighing over sus kilograms, disappeared at rates far higher than background extinction rates. The losses were staggering. In North America, sus genera of large mammals went extinct, including mammoths, mastodons, giant ground sloths, horses, camels, saber-toothed cats, short-faced bears, dire wolves, American cheetahs, giant beavers. In South America, the toll was even higher, over Wusser's genera lost, including all the giant ground sloths, the glyptodonts, the giant armadillos, the terror birds, the native horses and camels. In Australia, the extinctions occurred earlier, starting perhaps Wusserling years ago, when humans first arrived. Diprotodonts, giant kangaroos, giant wombats, marsupial lions, all disappeared within a few thousand years of human colonization. Europe and Asia lost fewer species, but still suffered significant extinctions. Woolly mammoths, woolly rhinos, cave bears, cave lions, giant deer, all vanished. In Africa, extinctions were less severe, but some large species still disappeared. What caused these extinctions? This question has been debated for decades, and there's still no consensus, though most scientists believe a combination of factors was responsible: climate change, human hunting, and the interaction between the two. The climate change hypothesis points to the dramatic environmental changes at the end of the Ice Age. As the climate warmed, vegetation zones shifted, the mammoth steppes disappeared, habitats fragmented. Species adapted to cold, dry conditions found themselves in a warming, wetter world, with different food sources, different vegetation. Some species couldn't adapt. Woolly mammoths, for instance, were specialized for grazing on dry, productive grasslands. As forests expanded and grasslands shrank, mammoth habitat declined. Populations became smaller, more fragmented, more vulnerable to genetic problems and local catastrophes. But climate change alone doesn't fully explain the pattern. Previous interglacials, warm periods between glaciations, didn't cause mass extinctions. Mammoths and other megafauna had survived multiple previous warm periods. Why did they go extinct this time? Oink. This is where humans enter the picture. The overkill hypothesis, proposed by Paul Martin in the Lickers, suggests that human hunting was the primary cause of megafaunal extinctions. Humans were efficient hunters, capable of killing large animals, and many megafauna had no prior experience with human predators. Woodies predators is where humans enter the picture. The overkill hypothesis, proposed by Paul Martin in the Lickers, suggests that human hunting was the primary cause of megafaunal extinctions. Humans were efficient hunters, capable of killing large animals, and many megafauna had no prior experience with human predators. They were naive, lacking the wariness that might have allowed them to survive. The timing supports this hypothesis. In Australia, extinctions coincide with human arrival around Wusserling years ago. In the Americas, most extinctions occurred between Wusserling and Surling years ago, shortly after humans crossed the Bering Land Bridge and spread through the continents. In Madagascar, large animals survived until humans arrived about Erling years ago, then disappeared within centuries. In New Zealand, the massive flightless birds called moa survived until Polynesian settlement around Sambide CE, then went extinct within Urbeck years. This pattern, extinctions following human arrival, is compelling, but the mechanism is debated. Did humans hunt these species to extinction directly, or did they disrupt ecosystems in ways that made survival impossible? Direct hunting could have been devastating. Large mammals reproduce slowly. Elephants, for instance, reach sexual maturity at Certisuwu years and have long gestation periods. Mammoths likely had similar life histories. If humans killed even a small percentage of the population each year, more than the birth rate could replace, populations would decline, eventually collapse. Computer models suggest that even low hunting pressure, killing just a few individuals per year per human group, could drive megafauna to extinction within centuries or millennia. Humans were effective hunters. Archaeological sites show evidence of mammoth kills, mammoth bone deposits with butchery marks, tools made from mammoth ivory. But was hunting alone sufficient? Some scientists argue for a more complex picture. Humans didn't just hunt. They altered landscapes through fire. Indigenous peoples worldwide used fire as a tool, burning grasslands to encourage new growth for game, to clear underbrush, to drive animals during hunts. In Ice Age environments, fire could have dramatically altered vegetation. Burning the mammoth steppes might have favored certain plant species over others, changing the productivity of grasslands, affecting herbivore populations. Some researchers suggest that humans set fires contributed to the disappearance of the mammoth steppes, transforming them into less productive ecosystems that couldn't support large herds. And then there's the hyperdisease hypothesis, proposed by Ross McPhee. This suggests that humans or their companion animals brought diseases to the Americas and Australia, diseases to which native megafauna had no immunity. Epidemics swept through populations, driving them to extinction. This hypothesis is harder to test. Diseases don't leave obvious traces in the fossil record, but it's plausible. We know that introduced diseases have devastated populations throughout history, from the plague in medieval Europe to smallpox among indigenous Americans after European contact. Most likely, the truth involves multiple factors working together. Climate change stressed populations, fragmenting habitats, reducing food availability. Human hunting added additional pressure, killing animals faster than populations could recover. Human-induced fires altered landscapes. Perhaps diseases played a role. These factors together, compounding, pushing populations past the point of no return. The extinctions weren't instantaneous. Some species survived longer than others. Mammoths, for instance, persisted on isolated islands long after they disappeared from the mainland. On Wrangel Island in the Arctic Ocean, a population of woolly mammoths survived until about Su-Ling years ago, isolated from humans, living on a small island where they evolved into a dwarf form. But eventually, even these refugia failed. The mammoths on Wrangel Island disappeared, possibly due to inbreeding, genetic problems, environmental changes, or human arrival. The last mammoths died while the pyramids were being built in Egypt, while civilizations flourished in Mesopotamia and China. The loss of the megafauna transformed ecosystems. Large herbivores shaped landscapes through their feeding, trampling, nutrient cycling. Their extinction released ecosystems from these pressures, allowing different vegetation to flourish, different fire regimes to establish, different ecological balances. Some scientists argue that the loss of megafauna changed the carbon cycle, affecting global climate. Large herbivores keep grasslands open by grazing and trampling. Without them, forests expand, and forests store more carbon than grasslands, potentially drawing company air from the atmosphere, contributing to cooling. Whether megafaunal extinction significantly affected climate is debated, but it's clear that their loss impoverished the world. The diversity of large mammals that existed during the Ice Age was extraordinary, rivaling or exceeding modern Africa. That diversity is gone, and we live in a diminished world because of it. Understanding these extinctions matters for conservation today. We're living through another extinction crisis, the sixth mass extinction, driven by human activities, habitat destruction, overhunting, climate change, introduced species, pollution, the megafaunal extinctions of the Ice Age are a warning, a reminder that even large, adaptable species can disappear when faced with rapid environmental change and human pressure. With the ice sheets retreated, the megafauna mostly gone, the world entered the Holocene, the warm interglacial period that's been our home for the past 3 years. This is the climate that allowed agriculture to develop, civilizations to rise, cities to flourish. Understanding the Holocene climate helps us understand what's normal, what's stable, what conditions enabled human civilization. The Holocene began with that abrupt warming at the end of the Younger Dryas. Temperatures in the northern hemisphere shot up perhaps 30 degrees Celsius in decades. In some regions, this wasn't gradual. It was rapid, dramatic, transforming ecosystems within human lifetimes. The early Holocene, from about 6 billion years ago, was generally warmer than today in many regions. This period is called the Holocene climate optimum or Holocene thermal maximum. Summer temperatures in the northern hemisphere were perhaps E2 degrees Celsius warmer than the pre-industrial average, driven by orbital variations that increased summer sunlight. The Sahara during this time was not a desert. It was a savanna with lakes, rivers, grasslands supporting hippos, crocodiles, elephants, and human populations. Rock art from the region depicts a landscape teeming with life, fishing scenes, cattle herding, abundant wildlife. This was the Green Sahara or African humid period. But around Ubat years ago, the African monsoon weakened, rainfall decreased, and the Sahara rapidly dried, becoming the desert we know today. This transition happened quickly, perhaps within centuries, forcing human populations to migrate to river valleys like the Nile, possibly contributing to the development of Egyptian civilization. Elsewhere, the climate was also changing. The monsoons in Asia were stronger during the early Holocene, bringing more rainfall to India, Southeast Asia, China. Lakes in currently arid regions were full. Vegetation zones continued shifting as climate stabilized. Sea level continued rising in the early Holocene as the remaining ice sheets melted, though more slowly than during the rapid deglaciation. By about bottling years ago, sea level was close to its current position, having risen about 8 meters since the last glacial maximum. The Middle Holocene, from about bottling to Sandling years ago, saw the development of agriculture and the first civilizations. Agriculture emerged independently in several regions: the Fertile Crescent in the Middle East, the Yellow River Valley in China, Mesoamerica, the Andes, West Africa, New Guinea, each developing different crops suited to local climates. Agriculture requires climate stability. You need predictable seasons, reliable rainfall or irrigation sources, temperatures suitable for crops. The Holocene provided these conditions. The climate wasn't static. There were droughts, floods, cold snaps, but overall it was remarkably stable compared to the Ice Age, allowing human populations to settle, to accumulate resources, and build they did. The first cities emerged in Mesopotamia around governing years ago. Egypt unified around the same time. The Indus Valley civilization flourished. Chinese dynasties rose. Minoans, Mycenaeans, later Greeks and Romans built empires around the Mediterranean. But the climate wasn't perfectly stable. There were fluctuations that affected these civilizations, sometimes catastrophically. Around C. Urbeck years ago, a severe drought struck the Middle East and Mediterranean, lasting perhaps Urbeck years. This drought is linked to the collapse of the Akkadian Empire in Mesopotamia, the end of the Old Kingdom in Egypt, the abandonment of settlements across the Levant. Similarly, around some years ago, another climatic shift, possibly involving drought and cooling, coincided with the late Bronze Age collapse. When multiple civilizations around the Mediterranean and Middle East collapsed simultaneously, the Hittites, Mycenaeans, several kingdoms in the Levant. This period saw widespread destruction, population decline, the disappearance of writing in some regions. These events remind us that even in the relatively stable Holocene, climate variations can stress societies, sometimes contributing to their collapse. Civilizations are resilient, but not infinitely so. Prolonged droughts, crop failures, famines can overwhelm social structures, leading to conflict, migration, collapse. The late Holocene, from about 7 years ago to the Industrial Revolution, saw continued climate variability. There was the Roman warm period, roughly Urbeck BCE to Subite CE, when temperatures in Europe were relatively warm, facilitating agriculture, supporting the expansion of the Roman Empire. Then came the medieval warm period, roughly Jobite to Ichen Sembai CE, another warm phase in the northern hemisphere. Vikings settled Greenland, which was greener than today, though never truly green, still mostly ice. Agriculture expanded in Europe. Civilizations flourished in the Americas, the Maya, the Chimu in Peru, Cahokia in North America. But the medieval warm period ended and the Little Ice Age began, roughly Ichen Sembai II, Ichen Babai Wusher CE. This was not an ice age in the glacial sense. Ice sheets didn't advance significantly, but temperatures dropped, winters were colder, summers shorter. Glaciers in the Alps and Scandinavia advanced. The Thames in London froze regularly, allowing frost fares on the ice. Crop failures became more common, contributing to famines. The causes of the Little Ice Age are debated. Volcanic eruptions, ejecting ash and sulfur dioxide into the stratosphere, block sunlight, causing cooling. Several large eruptions occurred during this period. Solar activity also varies, and the Little Ice Age coincided with periods of low solar activity, fewer sunspots, possibly reducing the sun's output slightly. The Little Ice Age affected societies. The Viking settlement in Greenland failed, unable to sustain agriculture in the colder climate. Famines in Europe contributed to social unrest, possibly to events like the French Revolution. In China, crop failures and harsh winters stressed the Ming dynasty, possibly contributing to its fall. But then, in the mid-Ichen Babits, temperatures began rising again, gradually warming through the late Ichen Babites and early Ichen Jobites. This warming continued, accelerating in the mid-Ichen Jobites, leading to the rapid warming we're experiencing today. And the Holocene, then, has not been perfectly stable. There have been warm periods, cold periods, droughts, floods. But compared to the Ice Age, compared to the dramatic swings between glacial and interglacial conditions, the Holocene has been remarkably stable, varying perhaps E or degrees Celsius globally, allowing human civilization to develop and flourish. That stability is now ending. We're pushing the climate beyond the range of natural Holocene variability into conditions the Earth hasn't experienced in millions of years. And we're doing it at a pace unprecedented in geological history. For most of human history, our impact on climate was negligible. We hunted, we gathered, we farmed, we built cities. But the atmosphere, the oceans, the ice sheets, these were forces beyond our influence. The climate changed, and we adapted or suffered. We didn't change it. That began to shift with the Industrial Revolution. Starting in the late Ichen Chibides, humans began burning fossil fuels, coal, oil, natural gas at increasing rates. These fuels, formed from ancient organic matter, buried and transformed over millions of years, release carbon dioxide when burned. Company, that had been locked away underground, now released into the atmosphere. At first, the amounts were small, But as industry expanded, as transportation shifted from horses to trains to cars to planes, as electricity grids spread, as populations grew, fossil fuel use exploded. The rate of company R emissions increased exponentially, particularly after World War II, in a period called the Great Acceleration. In inhabit glaciers, before the Industrial Revolution, atmospheric company was about megafauna parts per million, where it had been for thousands of years during the Holocene. By inhabit, it had risen to about 40 ppm. By inhabit glaciers, by ppm. By ppm. Today, in Artsenling Arswoods over, Seabite Arswool ppm and rising about Ardarnwoof ppm per year. This is higher than company R has been in at least 10 million years, higher than during the Pliocene, higher than at any time in human existence. And the rate of increase is unprecedented. Natural changes in company R, driven by orbital variations, volcanic activity, weathering, operate on timescales of thousands to millions of years. We've increased company R by 500 glaciers in less than 10 years. Company R is a greenhouse gas. It absorbs infrared radiation, heat emitted by the Earth's surface, trapping it in the atmosphere, warming the planet. This is basic physics, understood since the inhabits. More company R means more warming, all else being equal. And warming is exactly what's happening. Global average surface temperature has increased by about 85 degrees Celsius since the late inhabits, with most of that warming occurring since inhabit glaciers. This might not sound like much, but remember, global average temperature is a blunt. Regional changes are larger. The Arctic has warmed 2 degrees Celsius. Heat waves are more intense. Winters are milder. This warming is causing dramatic changes. Glaciers worldwide are retreating. The Arctic sea ice is shrinking, both in extent and thickness. The Greenland ice sheet is losing mass, melting at accelerating rates. The West Antarctic ice sheet is also losing mass, potentially unstable, at risk of collapse. Sea level is rising, currently about 100 millimeters per year, accelerating. Since the late inhabit, sea level has risen about to centimeters. This doesn't sound like much, but it's enough to increase coastal flooding, to threaten low-lying islands, to force adaptation in coastal cities. Because the oceans are warming, absorbing about 500 km of the excess heat trapped by greenhouse gases. Warmer water expands, contributing to sea level rise. Warmer oceans affect marine ecosystems, stressing coral reefs, altering fish distributions, changing ocean circulation patterns. The oceans are also absorbing about 500 of the company, or we emit, which dissolves in seawater, forming carbonic acid, lowering pH, making the ocean more acidic. This ocean acidification affects marine life, particularly organisms that build shells or skeletons from calcium carbonate, like corals, shellfish, some plankton. Precipitation patterns are changing. Some regions are getting wetter, others drier. Droughts are becoming more severe in some areas, like the Mediterranean, the American Southwest, parts of Africa. Extreme precipitation events, heavy downpours, are becoming more common as a warmer atmosphere holds more moisture. Hurricanes, typhoons, tropical cyclones, these aren't necessarily becoming more frequent, but they're becoming more intense, more destructive, fueled by warmer ocean temperatures. Ecosystems are shifting. Species are moving toward the poles, toward higher elevations, tracking temperatures. Forests are expanding in some areas, dying in others. The timing of seasonal events, migration, flowering, breeding is changing, sometimes causing mismatches between species that depend on each other. And extinctions are accelerating. We're losing species at rates, perhaps, E-batu, E-ling times higher than the background extinction rate, driven by habitat destruction, overhunting, pollution, invasive species, and increasingly, climate change. This is the sixth mass extinction, the first caused by a single species, us. The impacts on human societies are already visible. Heat waves kill thousands. Droughts reduce crop yields, contributing to food insecurity. Wildfires are more frequent, more intense. Coastal flooding forces, adaptation, seawalls, elevated buildings, sometimes retreat. But these are just the early impacts. We're committed to more warming even if we stopped all emissions today because the climate system has inertia. The oceans take decades to warm fully. Ice sheets take centuries to millennia to respond. We've locked in further changes, and we're not stopping emissions. Despite decades of warnings, despite growing awareness, despite renewable energy expansion, global company emissions continue to rise. We're still on a trajectory toward 10 degrees Celsius of warming by inhabit, possibly more if feedbacks amplify. 2 degrees doesn't sound catastrophic, but it's not a small change. It's roughly the difference between the Holocene and the Little Ice Age. It's enough to transform ecosystems, to threaten food security, to displace millions through sea level rise and extreme weather, to stress water resources, to increase conflict over resources. And there are tipping points, thresholds, beyond which changes become self-reinforcing, irreversible on human timescales. The collapse of the West Antarctic ice sheet, which could raise sea level by several meters, might be a tipping point. The shutdown of the Atlantic circulation, which would cool Europe dramatically, might be another. The transition of the Amazon from rainforest to savanna, releasing massive amounts of carbon, is another potential tipping point. We don't know exactly where these thresholds are. We're conducting an uncontrolled experiment on the only planet we have, pushing systems we don't fully understand, risking changes we can't reverse. Understanding past climate change gives us perspective on current changes, helps us predict future changes, reveals how the climate system works. Scientists study past climates using various methods: ice cores, ocean sediments, tree rings, cave formations, each providing different information about different timescales. Ice cores are among the most valuable. In places like Antarctica and Greenland, snow falls and accumulates, layer upon layer, compressing into ice. This ice traps bubbles of ancient air, preserving atmospheric composition. By drilling cores through the ice, extracting ice from different depths, scientists can analyze the composition of air from thousands of years ago. The longest ice core records extend back about babatling years in Antarctica. These cores show company levels, methane levels, temperature inferred from isotopes in the ice, dust levels, volcanic eruptions, all varying in cycles. The patterns are clear over the past babatling years. Earth has gone through 8 glacial interglacial cycles. Company varies between about Ebite Bashers ppm during glacial periods and Urbeg Bashers ppm during interglacials. Temperature varies by C2 degrees Celsius globally, more at high latitudes. These cycles are driven by orbital variations, Milankovitch cycles, with feedbacks amplifying the initial changes. When summer sunlight increases in the northern hemisphere, ice sheets melt, exposing darker land, absorbing more sunlight, warming further. The oceans release company as they warm, increasing greenhouse warming, amplifying the temperature rise. When summer sunlight decreases, ice sheets grow, reflecting more sunlight, cooling further. The oceans absorb company reducing greenhouse warming, amplifying the cooling. These feedbacks turn small orbital changes into large climate changes. But here's the crucial point. During all 8 glacial cycles, company never exceeded 70 ppm, never not in babatling years. And now in less than 70 years, we've pushed it to over Seabite War ppm, by Ursers, higher than the interglacial maximum, higher than at any time in these ice core records. Looking beyond ice cores, Scientists use other methods to reconstruct even older climates. Ocean sediments preserve shells of tiny organisms, foraminifera, that lived in ancient oceans. The isotopic composition of these shells reveals temperature and ice volume. By analyzing sediment cores from the ocean floor, scientists have reconstructed climate going back millions of years. Now, these records show that the current ice age, the Quaternary, began about 8 million years ago. Before that, during the Pliocene, climate was warmer, company are higher, ice sheets smaller. The Pliocene is relevant to our future because with company are above subite ppm, we're recreating Pliocene atmospheric conditions. Studies of Pliocene climate suggest that with company are around subite ppm sustained over long periods, global temperatures eventually stabilize to sand degrees Celsius warmer than pre-industrial. Sea level soar to Arsa meters higher as ice sheets fully respond. This is the equilibrium we're pushing toward if we maintain current company R levels. But we're not maintaining current levels, we're increasing them. If we continue on our current trajectory, we could reach Wubakor lobite ppm by Arsene Ebat, levels not seen since the Eocene, worse million years ago when there was no ice on Earth, when crocodiles lived in the Arctic, when sea level was tizers meters higher. The geological record also reveals past rapid climate changes, events when temperature changed dramatically over short periods. The Paleocene-Eocene thermal maximum, about Wuserlut million years ago, saw global temperatures spike by 2 degrees Celsius in perhaps Serling years, triggered by a massive release of carbon, possibly from methane hydrates. And this event caused ocean acidification, extinctions of marine organisms, disruptions of ecosystems. But even this event, catastrophic as it was, unfolded over Serling years. We're changing climate faster, much faster, over decades to centuries. Rapid changes have happened during ice ages, too. Dansgaard-Oeschger events, recorded in Greenland ice cores, show temperature swings of stirwal degrees Celsius in decades, dozens of times during the last glacial period. These were regional changes, affecting the North Atlantic and surrounding areas, driven by shifts in ocean circulation. And these events remind us that climate can change rapidly, that the system has modes, switches, tipping points. Understanding these past changes helps us identify risks in the present. Tree rings provide information about climate over recent centuries to millennia. Trees grow wider rings in good years, narrow rings in bad years. By analyzing ring patterns, scientists reconstruct precipitation, temperature, drought over centuries. These records show that the late Echenjobites and early Arsents have been exceptionally warm. The past few decades include the warmest years in at least Erling years, likely longer. The warming is unprecedented in the context of natural variability over the past millennium. Cave formations, stalagmites and stalactites preserve isotopic records of precipitation and temperature. Corals record ocean temperature and chemistry in their skeletons. Pollen preserved in lake sediments shows vegetation changes, revealing past climates. All these methods, these different archives, tell the same story. The climate has always changed, driven by orbital variations, volcanic eruptions, solar variations, changes in greenhouse gases. But the current change is different in its cause, a single species altering the atmosphere, and in its rate, faster than any natural change in millions of years. And the past also shows us that life adapts to climate change, but not without cost. Extinctions occur, ecosystems transform, species migrate or evolve or die. The pace matters. Slow changes allow adaptation. Rapid changes overwhelm species, ecosystems, sometimes civilizations. We're conducting the most rapid climate change experiment in geological history. The outcome is uncertain in details, but clear in direction: warming, disruption, stress on natural and human systems. Understanding the past doesn't give us precise predictions, but it gives us context, warning, and if we listen, wisdom. We stand at a critical juncture. The climate is changing, driven by our emissions, warming at a rate unprecedented in human history. We've already committed to further changes, but the future is not fixed. What happens next depends on choices we make now, on whether we reduce emissions, how much we reduce them, how quickly. There are two broad strategies for dealing with climate change: mitigation and adaptation. Mitigation means reducing greenhouse gas emissions, slowing the rate of warming, limiting future impacts. Adaptation means adjusting to changes already underway and those locked in, protecting communities, ecosystems, infrastructure. We need both. Even if we stopped all emissions today, we'd still face decades of further warming, sea level rise, ecosystem changes due to past emissions, and the inertia of the climate system. So adaptation is necessary, but unmitigated climate change would overwhelm adaptation efforts. There are limits to what we can adapt to, so mitigation is essential. Mitigation requires transforming energy systems. Currently, about 500% of global energy comes from fossil fuels, coal, oil, natural gas. These fuels power electricity generation, transportation, industry, heating. Replacing them requires massive expansion of low-carbon energy sources. Renewable energy, solar and wind primarily, has expanded rapidly over the past decade. Costs have fallen dramatically. In many regions, new solar and wind installations are cheaper than new fossil fuel plants. But renewables are intermittent, they need storage, grid integration, backup capacity. Battery technology is improving, costs falling, enabling storage of solar energy for nighttime use, wind energy for calm periods. Other storage technologies are being developed: pumped hydro, compressed air, hydrogen, thermal storage. Nuclear energy is low carbon, providing steady baseload power, but it faces challenges: high costs, long construction times, waste disposal, public opposition, risks demonstrated by accidents like Chernobyl and Fukushima. Hydroelectric power is important in some regions, but limited by geography, by environmental impacts on rivers and ecosystems, by vulnerability to drought. Transportation is challenging. Electric vehicles are expanding, powered by increasingly clean electricity grids. But aviation and shipping are harder to decarbonize, likely requiring sustainable fuels, possibly hydrogen or biofuels. Industry poses challenges. Cement production releases company R from the chemical process itself, not just from fuel combustion. Steel production requires high temperatures currently provided by coal. These sectors need new technologies, possibly carbon capture and storage. Agriculture contributes about a quarter of global greenhouse gas emissions, including methane from livestock, nitrous oxide from fertilizers company R from deforestation. Reducing these emissions requires changes in practices, improved fertilizer efficiency, dietary shifts toward less meat, protecting forests, restoring degraded lands. Forests are crucial. They absorb. Company are storing carbon in biomass and soil. Protecting existing forests, restoring degraded forests, expanding forests where possible, all contribute to existing forests, restoring degraded forests, extorting forest mitigation. But forests are under pressure from agriculture, logging, fires. Carbon capture and storage, CCS, involves capturing company R from power plants or industrial facilities, transporting it, injecting it underground into geological formations. This technology exists but is expensive, energy intensive, not widely deployed. direct air capture, removing company air directly from the atmosphere, is even more challenging, requiring large amounts of energy, currently very expensive. But it might be necessary to remove some of the company we've already emitted. All these solutions require investment, policy support, international cooperation. The Paris Agreement, adopted in Arsenling Isherwu, commits countries to limiting warming to well below our degrees Celsius, aiming for 1,5 degrees. Countries submit pledges, nationally determined contributions, outlining emission reduction plans, but current pledges are insufficient. We're on track for 1,5 degrees of warming by inhabit. Closing this gap requires stronger commitments, faster action, greater ambition. Adaptation means protecting communities from climate impacts. Sea level rise requires coastal defenses, seawalls, levees, beach nourishment, elevated buildings, or managed retreat, moving people and infrastructure away from coasts. Heat waves require cooling centers, public health campaigns, urban planning that reduces heat islands through trees, reflective surfaces, green spaces. Droughts require water conservation, efficient irrigation, drought-resistant crops, diversified water sources. Floods require improved drainage, wetland restoration to absorb water. Zoning that restricts development in floodplains. Wildfires require fuel management, prescribed burns, fire breaks, building codes that improve fire resistance. Ecosystems also need adaptation support. Protected areas, corridors connecting habitats, restoration of degraded lands, all help species migrate and adapt. But there are limits. Some species can't migrate fast enough, can't adapt quickly enough, and will go extinct. Climate change is not a distant future problem. It's happening now. People are dying in heat waves, losing homes to wildfires and floods, suffering crop failures and water shortages. The impacts are unevenly distributed. Poor countries, low-lying islands, arid regions, these face the greatest threats, though they've contributed least to emissions. Climate justice demands that wealthy nations, which industrialized early, emitting most of the historical greenhouse gases, support poor nations. This includes financial support, technology transfer, capacity building, but justice also applies within nations. Climate impacts hit the poor hardest, those with fewer resources to adapt, living in vulnerable areas, depending on climate-sensitive livelihoods like agriculture. Addressing climate change must address these inequities. The challenge is enormous. We need to transform energy systems, economies, societies in decades while lifting billions from poverty, while protecting ecosystems, while maintaining social stability. It's unprecedented, but it's possible. We have the technologies: solar, wind, batteries, electric vehicles, efficient buildings. These all exist, improving rapidly. What we need is political will, social commitment, investment, policy frameworks that incentivize clean energy and penalize emissions. We also need cultural shifts. Consumption patterns in wealthy nations are unsustainable, reducing consumption, shifting towards services rather than goods, valuing experiences over possessions. These can reduce emissions while improving quality of life. Individual actions matter: choosing clean energy, reducing meat consumption, using public transport, flying less, supporting climate policies, all contribute. But individual actions alone are insufficient. We need systemic change, policy changes, corporate responsibility, international cooperation. The climate crisis is also an opportunity. Transitioning to clean energy creates jobs, reduces air pollution, improves health, enhances energy security. Protecting forests preserves biodiversity, supports indigenous communities, provides ecosystem services. Building resilient infrastructure protects communities, reduces disaster costs. We can choose a future where energy is clean, abundant, cheap, where cities are green, livable, connected, where ecosystems are protected, biodiversity thrives, where societies are equitable, resilient, sustainable, or we can continue on the current path toward a hotter, more chaotic, more dangerous world. The choice is ours. The window for action is narrowing. Every year of delay makes the challenge harder, the impacts worse, the solutions more expensive. But the window is still open. We still have time, barely, to limit warming, to protect what we value, to build a livable future. We've journeyed through time tonight, from the warmth of the Pliocene through the ice of the glacial periods, through the extinctions of the megafauna, through the stable Holocene that enabled civilization, to the unprecedented changes of the present. The story of climate is a story of constant change. Ice sheets advance and retreat. Sea levels rise and fall. Species evolve, adapt, migrate, or go extinct. Ecosystems transform. The Earth is never static, never in perfect equilibrium. Change is the only constant, but the pace matters. Natural climate changes unfold over thousands to millions of years, giving species time to migrate, to adapt, to evolve. Ecosystems shift gradually, life persists. What we're doing now is different. We're changing climate in decades, 100 times faster than the Ice Age transitions, 1,000 times faster than the orbital cycles. We're pushing company ARTA levels not seen in millions of years. We're testing the limits of adaptation, of resilience, of survival. The Ice Age world was harsh, but it was stable within its cycles. Mammoths, woolly rhinos, cave lions, they thrived for hundreds of thousands of years, adapted to cold, to the mammoth steppes. They survived multiple glaciers. What they couldn't survive was the combination of rapid climate change and human hunting pressure. The ecosystem they depended on disappeared too quickly. They couldn't adapt. We're creating similar conditions now. Ecosystems worldwide are under pressure from habitat destruction, overexploitation, pollution, invasive species, and now rapid climate change. Many species won't make it. Ecosystems will transform. The world will be diminished. But it doesn't have to be catastrophic. We're not mammoths. We have knowledge, technology, the capacity for foresight and planning. We can choose to reduce emissions, to protect ecosystems, to adapt to unavoidable changes, to build a sustainable future. The past teaches us that climate shapes everything. It shaped evolution, creating the conditions for life to diversify. It shaped landscapes, carving valleys, depositing sediments, creating the geography we know. It shaped human history, enabling agriculture, stressing civilizations, forcing migrations, and now we're shaping climate. We've become a geological force, altering the atmosphere, the oceans, the land surface at a scale and pace unprecedented. We're living through a transition as significant as the end of the Ice Age, but compressed to a single human. And our children will live in a world different from ours, just as our world is different from our grandparents. The question is how different, how disrupted, how dangerous. That depends on what we do now. The ice cores, the ocean sediments, the rocks, they all speak clearly. They tell us that company or drives temperature, that climate responds to forcing, that changes cascade through systems, that tipping points exist, that what we do matters. They also tell us that Earth has been through dramatic changes before and survived, that life is resilient, adaptable, persistent. After every mass extinction, life recovers, diversifies, fills the empty niches. It takes millions of years, but it happens. So, but we don't have millions of years. We have decades to make choices that will determine the future for centuries. We don't get to wait for natural recovery. We live in the present with responsibilities to future generations, to the ecosystems we depend on, to the planet that is our only home. Nay, I started this journey by asking if you'd ever looked at a glacier and wondered what stories it holds. Now, having walked through ice and time, through extinctions and adaptations, through human triumphs and challenges, I hope you see those stories differently. In those glaciers, retreating now, melting faster each year, they're not just ice, they're libraries burning. They hold records of atmosphere from thousands of years ago, records we're reading just in time before they disappear. Each glacier that melts is history lost, data erased, a witness to Earth's past silenced, but they're also warnings. Their retreat tells us the climate is changing, warming, responding to our emissions. The ice doesn't lie. It doesn't have political motivations or economic interests. It simply responds to temperature, to physics, to reality. The mammoths couldn't speak for themselves. They couldn't warn us what happens when climate changes too fast, when ecosystems transform beyond adaptation, when the world you're built for disappears. But their bones speak, their extinction speaks, the empty mammoth steps speak. We're the storytellers now. We're the ones who have to decide what story we tell with our actions, with our choices, with how we respond to the knowledge we have. Do we tell a story of foresight and action, of transformation and adaptation, of a species that looked at the precipice and stepped back? Or do we tell a story of warning ignored, of knowledge without action, of a civilization that had every advantage and squandered it? The climate will change regardless. That's guaranteed. We've already put enough greenhouse gases in the atmosphere to ensure decades of further warming. Glaciers will continue melting. Sea levels will continue rising. Heat waves will continue intensifying. Some species will go extinct. Some ecosystems will transform. But the degree of change, the severity of impacts, the suffering or prosperity of future generations, these are not fixed. They depend on what we do in the next few years, the next decade, the next generation. Every fraction of a degree matters. Every ton of company matters. Every forest protected, every coal plant retired, every electric vehicle, every policy change, every choice to act rather than delay, all of it matters. The Ice Age ended 38 years ago, but its legacy surrounds us. The landscapes carved by glaciers, the Great Lakes, the fjords of Norway, the valleys of the Alps, all products of ice. The fertile soils deposited by glaciers, supporting agriculture across vast regions. The extinctions that impoverished ecosystems, but also created niches for species that survived, and us. We're Ice Age survivors, descendants of people who endured the harshest conditions, who adapted, who innovated, who persisted. That resilience, that capacity to adapt, to overcome challenges, to work together for survival, it's in us. But we also inherited the Ice Age extinctions, the lesson that even large, successful species can disappear when conditions change too fast. We inherited the abandoned cities of the Bronze Age, the lesson that civilizations can collapse when climate stresses resources, when droughts persist, when social structures fracture. We have the knowledge that previous generations lacked. We understand the climate system. We can measure company in the atmosphere, temperature in the oceans, ice loss from satellites. We can model future changes, predict impacts, identify solutions. We have technologies our ancestors couldn't imagine. We can generate electricity from sunlight and wind. We can store energy in batteries. We can communicate instantly across the planet, sharing knowledge, coordinating action. What we sometimes lack is the will, the urgency, the sense that this moment matters, that history is watching, that future generations will judge us not by our words, but by our actions. There's something profound about living through a transition, about being present at a moment when everything changes. Most people throughout history lived in relative stability. Their world, their climate, their environment, it stayed roughly the same from their birth to their death, generation after generation. We don't have that luxury. We're living through the fastest climate change in human history, possibly in millions of years. The world our children inhabit will be fundamentally different from the one we grew up in, and the world their children inhabit will be even more different, changed by what we do or fail to do now. And this is the weight of now. This is the responsibility we carry, whether we asked for it or not. We're the generation that has to decide. We're the ones standing at the junction, able to choose paths, to influence outcomes, to shape the future in ways that people a few decades from now won't be able to. Every previous generation of humans lived within the climate system, subject to its changes, adapting or perishing. We're the first generation that's changing the climate itself, that has become a force of nature, a geological agent. That power comes with consequences. We can't claim ignorance. We can't say we didn't know. The science has been clear for decades. The warnings have been loud, consistent, increasingly urgent. We know what's happening. We know what's coming. We know what needs to be done. The question is whether we'll do it, whether we'll overcome the inertia, the economic interests, the political divisions, the short-term thinking that has delayed action for so long. History is full of moments when people faced existential challenges and rose to meet them. The world wars required total mobilization, societies transforming overnight, directing all resources toward survival. The abolition of slavery required people to fight against powerful economic interests, to recognize the humanity in those they'd been taught to see as property. The civil rights movement required courage, persistence, moral clarity against entrenched injustice. Climate change is a different kind of challenge. It's slower, more abstract, easier to ignore day to day. The enemy is not a foreign army or an evil dictator. It's our own consumption, our own systems, our own choices, but the stakes are comparable. We're talking about the habitability of the planet, the survival of ecosystems, the stability of civilizations, the future of billions of people. And this isn't just an environmental issue. It's not just about polar bears and coral reefs, though they matter too. It's about food security and water availability. It's about whether coastal cities can survive or must be abandoned. It's about whether agricultural regions can continue feeding populations or fail, triggering famines. It's about whether we maintain a world that's livable, productive, stable. The solutions exist. The technologies are proven. What's needed is deployment at scale, investment, policy support, social will. And here's the hopeful part, it's happening. Solar and wind energy are expanding faster than any previous energy transition. Electric vehicles are moving from niche to mainstream. Countries are setting ambitious climate targets. Cities are implementing adaptation plans. Young people are demanding action. The transition has begun. The question is whether it's happening fast enough, whether we can accelerate it, whether we can make it comprehensive enough to avoid the worst outcomes. And we can't stop climate change entirely. The climate has always changed and always will. But we can influence how much it changes, how fast, how disruptive. We can choose between 1.5 degrees of warming and centigrades, between manageable impacts and catastrophic ones. Every culture has flood myths. The Epic of Gilgamesh, the biblical story of Noah, Greek myths of Deucalion, Hindu stories of Manu, indigenous American stories, Aboriginal Australian stories, all describe catastrophic floods that destroyed the world with only a few survivors. These stories might preserve memories of real events. Floods caused by sea level rise at the end of the Ice Age, by the breaching of ice dams, by tsunamis. They might remember the drowning of coastal settlements as seas rose. Ebite arsos meters, slowly enough that no individual saw the change, but fast enough that societies over centuries had to retreat inland. Or they might simply recognize that floods happen, that water is powerful, that nature can overwhelm human constructions. Either way, these stories serve a function. They remind us that we're vulnerable, that the world can change, that catastrophes happen. They encode wisdom about preparing, about resilience, about the importance of foresight. What stories will we tell about climate change? What myths will future generations create to explain this moment, this transition, this choice we faced? Will they tell stories of the Great Mobilization, when humanity recognized the threat and acted, transforming energy systems, protecting ecosystems, building a sustainable world? Stories of cooperation and innovation, of sacrifice for future generations, of wisdom overcoming short-term greed? Or will they tell cautionary tales of a civilization that knew what was coming but couldn't act, that had all the knowledge and tools but lacked the will, that sacrificed the future for the present? The story isn't written yet. We're writing it now, with every policy enacted or blocked, with every coal plant built or closed, with every forest cleared or protected, with every choice to act or delay. And here's what matters. Individual chapters don't determine the ending. Setbacks don't mean failure. Progress isn't linear. The climate movement has won battles and lost battles, made advances and suffered defeats. That's normal. That's how change happens. What matters is the overall direction, the accumulation of changes, the persistence over time. What matters is not giving up, not accepting defeat, not falling into cynicism or despair. Because despair is a luxury we can't afford. It's self-fulfilling. If we believe nothing can be done, then nothing will be done. If we believe change is impossible, we won't work for it. But hope, realistic hope grounded in evidence, that's powerful. Hope drives action. Hope builds movements. Hope changes the world. And there's reason for hope. The transition to clean energy is accelerating. Costs are falling, technologies are improving, public awareness is growing. Young people especially understand the stakes, demand action, won't accept business as usual. The political landscape is shifting. Climate is moving from fringe issue to central concern, affecting elections, driving policy, forcing corporations to adapt. Nature still retains resilience. Ecosystems, when protected, can recover. Forests can regrow, species can adapt, oceans can heal, and humans are capable of extraordinary things when motivated. We've overcome challenges before. We've transformed societies, rebuilt after wars, cured diseases, achieved things that seemed impossible. Climate change is solvable. It's difficult, unprecedented in scale, requiring global cooperation and sustained effort over decades. But it's not impossible. We have what we need. We just need to use it. Think about what we've inherited from past generations. The accumulated knowledge of thousands of years, the agricultural practices that feed billions, the technologies that power modern life, the art and music and literature, the cities and infrastructure, the institutions and laws. Think about the natural world we've inherited, the forests and oceans, the rivers and mountains, the incredible diversity of life, the stable climate of the Holocene that enabled everything we've built. All of this is an inheritance passed down through generations, each adding something, preserving something, handing it forward. And what will we pass on? What inheritance will we leave? We can't leave a pristine planet. That ship has sailed. We've already altered the atmosphere, the climate, the ecosystems. The extinctions have already begun. The glaciers are already melting. But we can leave a fighting chance. We can leave technologies that enable sustainability. We can leave protected ecosystems that preserve biodiversity. We can leave knowledge and institutions that facilitate adaptation. We can leave a world that's still livable, still productive, still capable of supporting civilization. Or we can leave a depleted world, stripped of resources, scarred by climate chaos, impoverished in species and ecosystems, burdened with problems we created but didn't solve. The choice seems obvious when framed this way. Who would choose the second option? Who would deliberately harm future generations? But that's the insidious thing about climate change. The harm is indirect, delayed, diffuse. The people making decisions today won't suffer the worst consequences. Those fall on people not yet born, on other species, on distant communities. It's easy to prioritize the present when the future seems abstract. It's easy to discount long-term risks when short-term costs are concrete. It's easy to think someone else will solve it, that technology will save us, that it's not really as bad as scientists say. But the future isn't abstract. It's where our children will live. It's where all the people who come after us will live. They're real, even if they don't exist yet. They'll inherit whatever we leave them. They'll judge us by what we did and didn't do, and they'll ask questions. They'll ask why we didn't act faster when we knew what was happening. They'll ask why we allowed extinctions when we could have prevented them. They'll ask why we prioritized short-term profits over long-term survival. We should have answers, good answers, answers that show we tried, that we cared, that we did our best with the knowledge and resources we had. Right now, I'm not sure we have those answers. We're not doing our best. We're not acting with the urgency the situation demands. We're still expanding fossil fuel infrastructure, still clearing forests, still increasing emissions in many countries. But we can change that. It's not too late for better answers, for a better legacy, for a future we can be proud to pass on. Okay, one final thought before we end this journey. Let's take the long view, the geological perspective, the view from millions of years in the future. From that perspective, what we're doing is creating a boundary layer in the geological record. So a thin line marking the transition from the Holocene to whatever comes next, what some call the Anthropocene, age of human influence. And future geologists, if they exist, will be able to identify this layer clearly. They'll see a spike in company R recorded in ice and sediments. They'll see evidence of mass extinctions in the fossil record. They'll see radioisotopes from nuclear testing. They'll see plastics and concrete and altered minerals. They'll see the end of the stable Holocene and the beginning of something new. What they won't see, what no amount of geological detective work can reveal, is why. They won't know whether we acted out of ignorance or willful disregard. They won't know whether we tried to stop it or accelerated it. They won't know our motivations, our debates, our failures and successes. And they'll just see the results, the changed chemistry, the extinct species, the altered climate, unless we leave records, unless we preserve knowledge of this time, of what we did and why, unless we write our story so thoroughly that it survives however long humanity does. And what do we want that story to say? We were the species that woke up, that recognized its impact on the planet and changed course, that valued the future enough to sacrifice for it, that used its intelligence and technology not just for exploitation but for preservation. We were the generation that faced the greatest challenge in human history and rose to meet it, that transformed energy systems in decades, that protected what could be protected and adapted to what couldn't be avoided, that built a foundation for a sustainable future. That's the story worth telling. That's the legacy worth leaving. That's the inheritance worth passing on. The climate has a memory longer than civilization. It remembers the ice ages and the warm periods, the extinctions and the diversifications, the rises and falls of species and ecosystems. It will remember us too. It will record our actions in ice and sediment, in chemistry and biology, in the configuration of life on Earth millions of years hence. Now, what we want it to remember is not that we existed, that's inevitable, but how we existed, whether we were wise enough to change, whether we cared enough to try, whether we loved the world enough to protect it. The ice is melting. The climate is changing. The future is uncertain, but it's not fixed. We still have agency. We still have choice. We still have time, barely, to write a better ending. And so look at those glaciers, those rivers of ice flowing down mountains, holding stories from thousands of years ago. Look at them and remember, we're part of this story too. We're writing the next chapter, and it's not written yet. What happens next is up to us. A thank you for walking through time with me tonight, through ice and warmth, through extinctions and survivals, through challenges and choices. I hope you see the present differently now, connected to deep time, to geological forces, to the long arc of climate and life on Earth. If this exploration, if you found value in understanding where we've been and where we might be going, I'd be grateful if you shared this with others who might benefit. Knowledge shared is knowledge multiplied, and we need as many people as possible understanding these stories, these lessons, these choices The Ice Age is over. The Holocene is ending. What comes next is being written now by all of us. With every choice we make it count.